Today we begin our work on binomial expansions, and then later we'll be looking at their relationships with combinatorics. So firstly, what is a binomial? Well, bi just means two, and the nomial part actually stands for name. So it's really just something with two parts to its name. And in maths, we say it's an algebraic expression with two terms. So those two terms can be anything really, and they'll be added or subtracted from one another. So then a binomial expansion is just the expansion of the brackets when we raise a binomial to some power. Now we're already really familiar with what to do when we're raising a binomial to the power of 2, and we know how to expand our brackets in that case. But we'll be looking at ways that we can simplify the expansions when we've raised our binomial to some larger power. So let's revise the method that we use when we're expanding brackets and see how we can use that method to raise a binomial to higher powers than just 2. Now, when we're doing these ones, we're already familiar with the FOIL method. We do the firsts, that means x times x. We do the outsides, that means x times y. We do the insides, y times x. And we do the lasts. So we can do all those 4 things in any order, and you can see that we get 4 terms. 2 of those terms, the insides and the outsides, come together to make what we call the middle term, and being like terms, we can add them together and we get our expansion like that. Raising a binomial expression to the power of 3 really just requires us to break it down and say, look, if we're multiplying and the bases are the same, then all we need to do is add the indices. And really we have one lot of the binomial expression multiplied by that same expression squared. So that gives us a method. It's not quite the FOIL method because there'll be more than 4 parts here, but basically we need to multiply the x by all 3 parts in here and then multiply the y by all 3 parts. Now that gives us 6 terms, and you'll notice that I've written them out kind of systematically, always putting the x's before the y's just so that it's easier for me to spot my like terms. So simplifying on the next line, I've got only one term that has x cubed in it and one term that has y cubed. But when I look at these x squared y's, I've got 2 of them here and another 1 there. That makes 3 altogether. And if I look at the xy squareds, I've got 1 here and 2 there. So I've got 3 of those as well. And we get this expansion. Raising a binomial expression to the power of 4 means that I just need to raise one lot of that binomial expression to that same expression cubed. And now that I've got the expansion cubed, I can use the same sort of method as I did last time. There's going to be a lot more parts though, you can see. So I need to do x multiplied by all 4 of these terms, and then y multiplied by all 4. And that's going to give me 8 terms altogether. So here are my 8 terms, and once again, some of them will be like terms. The first and the last one won't be, but you'll find that some of the other terms are like terms and they can be brought together to simplify the expansion. Now, I think you can see here that there's quite a lot of work, even when we're only raising a binomial expression to the power of 4. So imagine raising it to the power of 20 or something like this. Working longhand is clearly going to be quite frustrating. So clearly, we need a better method. Now, you'll have noticed that there's going to be repeating patterns in these expansions. So maths is all about the study of those patterns so that we can work a little bit smarter and not have to go through this laborious process every time. So let's have a look at what those patterns really are. Okay, so here are a bunch of expansions. Now I've used colour so that you can clearly see what's happening with the x part and what's happening with the y part in each expansion. I want you to pause the video in a moment so that you can take some time to copy this down. Feel free to copy it just in one colour, but actually examine it on your screen here with the colours, and I want you to see how many patterns you can find. Pause the video now. So I'm assuming that you've copied all of this down now, perhaps just in one colour, and you've had a look at some of the patterns. Let's have a look at what they are. Well, if there's x plus y raised to the power of n, then what we can see is that there's always going to be n plus 1 terms. We can see that here. When we're raising to the power of 0, there's 1 term. With 1, there's 2 terms. 2, there's 3 terms, and so on. The other thing that's really obvious is that the powers of x start with the same power that we're raising the whole binomial expression to. So here we've got x to the power of 1. And when we're raising to the power of 2, we're starting with x squared. X to the power of 3, we're starting with x cubed, and so on. But those powers of x decrease. We have x squared, x to the power of 1, and then there's no x's here at all. Effectively, that's x to the power of 0. And similarly, x cubed, x squared, x to the power of 1, x to the power of nothing. 4, 3, 2, 1, etc. So they're always decreasing, starting with the highest power and going down to a power of 0 in the last term. On the other hand, the powers of y increase when we write them out sequentially like this. So we're starting off with that first term being no y's at all, and y to the power of 0 is just 1. So effectively this first term is y to the power of 0, but the second term is y to the power of 1, and then y to the power of 2. And if we keep going, we'll get y to the power of 3, y to the power of 4, etc., etc., until we always end up with our last term being y to the power of that same thing that the whole binomial expression was raised to. Now, the other important thing to note, we know what's happening to the x's, we know what's happening to the y's, but now we have to have a look at the coefficients of each term. And there's a pattern to those too. They're the numbers that you can find in Pascal's triangle. So to make them more obvious, let's put in a 1 where we have no coefficient there at all, because effectively that is a 1. So that will be on all of these here. And we get these numbers, which should be somewhat familiar to you. Now, you might remember doing an activity with Pascal's triangle back in year 7, or perhaps you've seen it sometime since then, or maybe today is the first time you've encountered it. Either way, this set of numbers is very famous in maths because it pops up all over the place in lots of different topics. Curiously, it wasn't actually Pascal who discovered it. It was first noted by an Indian mathematician called Pingala in the 2nd century BC. But in the 1650s, Pascal did quite a lot of work with this set of numbers, so since then it's been known, perhaps a little unfairly to Pingala, as Pascal's triangle. Now, a few things to note about it. Obviously, there's a 1 going all the way down each diagonal, so we can see that each row starts and ends in a 1. We can also see that each row is palindromic, which just means that it's the same backwards as forwards. It's got that symmetry as you work in from the edges. And we saw that same thing with the coefficients of our binomial expansions. And in fact, these are the coefficients of each binomial expansion. Which one? Well, the power, as I've written down the side here, if we call it n, when we raise a binomial expression to the power of n, will give us the row that we need to find the coefficients of each term in that expansion. Now, the other thing you'll notice is that each number is the sum of the two numbers diagonally above. So if we take a number, say this 10, then it is the sum of the 6 and the 4. So pause the video now so that you can jot down Pascal's triangle. Nice to have a good copy of it in your book. And you can use this feature to create the row for n equals 9, adding each digit above to find the digits in that row. Now, there are lots of other interesting patterns in Pascal's triangle. For instance, you might have noticed the triangular numbers working their way down this diagonal, but that's not super relevant to our topic today. The other thing that you might notice is that this pattern, very simple here, of 1, 2, 3, 4, 5, 6, going down here, in fact, is the second number in each row. That is a really good hint as to what your power is, okay? So if you're looking for the correct row and you're generating, say, an expansion of x plus y to the power of, say, 7, it's nice and easy if you've got a copy of Pascal's triangle to have a look at to know that you'll want this row here that has the second digit as the 7. Now, I mentioned earlier that binomial expansions and Pascal's triangle are all very closely linked to combinatorics. How? Well, we've already seen this formula before in our unit on combinatorics. Remember that the C stands for combinations here, although we say n choose R because conveniently C also stands for choose. We can also call this n choose R and write it with this notation, and we know the formula for working out n choose R longhand. Now, even though you've already copied this formula down back when we studied combinatorics, I want you to copy it down again in today's notes so that it really highlights for you that this formula is important with our work on Pascal's triangle and binomial expansions as well. And this is why they're relevant. Those same numbers in Pascal's triangle can be written as n choose R numbers or as combinations. Now, this makes so much sense the more we look at it. And once we get into binomial probability, it will make even more sense. Now, when you're looking at the n number, And with our binomial expansions, we want that number because that's the number that our binomial has been raised to. We can see that in each case, the number that is there is the same number that we've got at the top of our n-choose-r, or our combination. So if you're thinking about choosing things and how many ways there are to make those choices, this makes a lot of sense. If you've got two things and you're looking at how you can make a subset of those two things, you can either choose nothing, you can choose one of the two items, or you can choose both of the two items. If you've got three items, you can either choose nothing, one, two, or three of them. And I think you can see here, we've already discussed the fact that choosing nothing is the same as choosing everything. And if you've got three items and you choose one of them, you've effectively not chosen two. So I think you can see there why we get that palindromic nature on each line. So take a moment now to pause the video and copy down the first part of Pascal's triangle. We don't need to go super far, but just enough so that we can see the pattern and we understand what's going on.